Hi everyone, welcome to Module 11 on containers. My name is Sebastian, and in this presentation we're going to take a look at different ways of isolating your computation environments and why that's a good idea. So specifically we're going to be talking about containers, and you've all encountered containers in your life before. And at the deep level, the things we're talking about today are really not that different from the real-life containers you've encountered, in the sense that they're used to contain things and isolate them from their surroundings, and transport things in containers so other people can unpack them and use them. And we're going to take a look at different ways that they can be useful to your research and for you to create reproducible compute environments for the type of works that you do. So after a brief introduction, we're going to look at virtual machines, which are a way of isolating compute environments that has been popular in the past and still has specific applications today. And then we're going to spend most of the time talking about what is known as containers, and specifically Docker, which is a suite of tools that is the most popular suite of tools to provide you access to containers and their functionality. And at the end, we're going to take a look at Singularity, which is a way of running these containers on supercomputers. Okay, so why should we isolate environments? You've probably already used some environments that are isolated with your Conda environments that you've been using over the course of the other modules. And there are a couple of good reasons, but I think one very important one is that you can specify what your environment should look like. And if you've done the setup instructions, you remember that there was an install command, and it told you in that command what modules of sort of Python libraries you should be installing. And if it specifies the version of these Python libraries, then really what this does is it describes the environment that should be created for you to run code in. And it can be very specific in that way. And that's very useful, one, if you want to give the product of your work to somebody else, for example, another colleague, and say, hey, run this code that I wrote, and in order to run it, you should create an environment that has the following properties. So install all these libraries, for example, specific versions, and this can get more complex. The other, almost more important reason is you should do it for yourself. You should describe the environment that you've been working in, because you might come back to a project a couple months from now, and it's not that rare to find that you can't run it anymore because something has changed and you don't really understand what or why, because you just ran a bunch of install commands and then forgot about it. So when you go and look at research artifacts or a paper that has accompanying code, you may find things like this, where this is a paper from our lab, and you see that there are these dependencies, and they tell you need to install these libraries, but not only the library, but also above a specific version. And when you do this, you will be able to run the code. So that's one important reason why you should describe your environment. Now, what does this have to do with isolation? Well, you can't just install these specific criteria and expect it to work for every project that you work on, right? Usually you work on separate projects. So the second point is you shouldn't be using the same environments for all of your projects. In fact, you should be using a separate environment for every project you work on. And this is a little XKCD comic that tries to illustrate this point. The maintainer of this library has made some fix, and now the CPU no longer overheats when you hold down the spacebar, and that sounds like a good idea, but turns out somebody actually built a workflow that relied on this specific bug, feature, property, and now their code doesn't work anymore, right? So from the perspective of longtime user 4, it would have been nice to have an isolated environment where they can stick to, I guess, 10.16 and don't have this fix. But there might be other projects that rely on, your CPU not overheating. And so now you already have a problem where you have conflicting requirements for different projects, and that means you need to isolate environments for different projects. And you can see this in real life where different projects have incompatible version requirements. So these are two that I've taken randomly of tools that are commonly used in your imaging. So CPAC and fMRI Prep are both pipelines. You can see here that they rely on NiPi versions that you can't resolve those in the same environment, right? They're different constraints. So again, you need to create two boxes for each of these so they can live with their specific needs. And then the last one, you may have already heard this, it's a very bad idea to install things into your system Python. That's why we start with the Conda or virtual Python environments at the beginning of the course. Because if you do install things into your system Python, those can again interfere with other things. Your system Python is actually used by a lot of applications, and if you just install everything there, you might break things, and that's not a good idea. So always use virtual environments when you work with Python. Now, a good analogy for me is if you are going to bake a cake, right? You have essentially the same thing. You want to do something, this is your code, and it has specific requirements, and that's your recipe. And one of the things that it requires is you say, oh, well, please heat the space that the cake is in to 163 degrees. Now, nobody would think that they do this in your global environment like this, right? You don't heat up your entire apartment because that's bad. There are other things in your apartment that don't like it when it's 163 degrees. So the way that we in our daily life fix this problem is by isolating things, right? So you might have an aquarium with some fish, and then you have a stove, and these two things have very different environmental needs. And so you put them in a box, and you make an environment in one box and a different environment in another box. And that's really very similar to what isolating environments means, just that you do it on a software level. Okay, so now that we have the big picture in mind, why don't we just stick to the Python virtual environments? They seem to be working pretty well. Why do we even need to bother with things like containers and all these complicated things that everybody needs to learn about? Well, as you may already know, Anaconda actually gives you more than just Python. So you can have some precompiled binary dependencies that Conda also provides for you. But they're very selected and curated for the type of data science needs that the Anaconda maintainers are trying to offer. And so really there are quite a bunch of binary dependencies, especially specialized ones like in neuroimaging, that you can't get via Conda. So if you look at the install instructions for fMRI Prep, for example, you need to install FSL. So that's a thing you won't get on Anaconda. Now, the second thing is that not everything is written in Python and R, which are the two main languages that Conda is supporting. So if you have something written in Julia or Go or JavaScript, God forbid, you have other libraries that you need to get, and you can't recreate an environment that needs these things via a Conda install command or Conda environment description. And your operating system has also packages, right? There are things that you install and occasionally update. If you're on Linux, you update your system dependencies, and that may change some underlying low-level library that you didn't even know, but actually has a pretty strong impact on your results. So you want to ideally also describe that part of your environment, which is the operating system that you haven't really even considered maybe. And the tricky part is that the same version problems that we saw before with the Python libraries can also apply to all of these things, right? There might be conflicts with different operating system library versions that interfere with your results. So really we want to capture ideally the entire compute environment. So again, we can share it with colleagues and we can keep it running for ourselves. So how do I describe a compute environment that includes FSL or AFNI or some specific version library? I cannot do this with Python virtual environments. I cannot do this with Conda. So in a way, what I have to do is I have to make boxes that contain operating systems. So how can I do that? And one of the ways to do this is with virtual machines. So the idea of virtual machines is that if I have to create different boxes for different operating systems and all the dependencies I want to install, then it would be great if I don't have to buy separate physical computers for each of these boxes. So in other words, if I want to install 2 different versions of Windows, I don't want to have to buy 2 different computers. Now, the way to do this with a virtual machine is that I have one computer with its hardware, CPU, memory, hard drive, all these things. And I now use a software application to make virtual copies of this physical hardware that I have, and show it to these virtual machine boxes on my host computer, so they think this is a unique piece of hardware that they have access to. And what this allows me to do is I'm now able to install operating systems in these virtual machines that are using the same physical hardware under the hood, but from the inside of these virtual machines, it looks like I'm on a separate computer, because there's absolutely nothing shared other than the hardware, and I can install anything that would run on my computer. That is a very useful property, because I can do things like, here I'm on a Mac, and I have 2 virtual machines. One of them is running another Mac operating system, but the other one is running Windows. And you can do the same on a Linux machine. You can run a virtual machine that has Windows, or on a Windows machine. The idea is always the same. You create virtual representations of the physical hardware on your host computer, and then you expose that hardware to the virtual machine, and then the virtual machine acts as a full computer, essentially. So everything you do with a normal computer, you can do with a virtual machine. Now, the way this works is that when you're on a physical computer, you have your hardware, and then you have this host OS, or operating system. And specifically what we're talking about here is called the kernel, and that is a type of software that knows how to talk to the hardware. So when you think about it, the fact that you can install, let's say, the same version of Windows on your laptop and on your colleague's laptop and on a desktop PC from a completely different manufacturer, and all of these things have different specific hardware installed in them from different manufacturers of CPUs or memory or hard drive. The fact that you can do this is because there's this software layer that knows how to talk to all of these pieces of hardware, and then creates an abstraction so that the applications that you install don't have to know whether they're running on a computer that is made by Dell or by Sony or by Lenovo. And so this is a really critical piece of software on your computer, this operating system kernel, and that's what you normally install when you install an operating system, plus a bunch of other things. Now, because you're in a virtual machine, and to you live on a real computer, you have to install this operating system and the kernel again, because here you're interfacing with virtualized hardware. And that's why this type of virtualization or isolation is called hardware virtualization. And the way you make one of these virtual machines is that you install on your host computer another piece of software. It's called the hypervisor. And this hypervisor is talking to its own kernel and is exposing the actual physical hardware on the host computer to these virtual machines, so that they then can have their own operating system or kernel talk to the virtualized version of this hardware. And there are some really attractive properties about this. So specifically, you're fully isolated from the host operating system. You share nothing except the hardware. And that's really helpful if you want to test things across many systems. So if you want to test that your software runs on Mac, Windows, and Linux, or on different versions of Windows, that's a good way of creating such a test environment. You create a bunch of these virtual machines, and you can then run these tests. It's also nice for system isolation, because the software that's running in the virtual machine has no way of breaking out of this box. It can only see its own virtualized hardware, and there's no way of it accessing things that are running on the host machine unless you explicitly enable this via some type of sharing method. Now, there are a bunch of downsides with these virtual machines, and that's why they're not used that much anymore, except for these specific cases where they're useful. One is that it doesn't really share resources with the host. So if you create a virtual machine, you have to allocate that hardware, or a portion of your hardware, a portion of your memory, number of cores in your CPU, exclusively to this virtual machine. So now they're blocked. Whether the machine uses them or not is not important. So if you have 10 virtual machines, you need to provide each of them with their own set of allocated resources. And so for a host machine, that can get quite expensive. You need to have a lot of resources to share them, to provide them to these virtual machines. They're also, because they're essentially working like full computers, they're quite slow to start, which may not matter so much in a research context, but if there are applications that need to launch and stop and resume these types of environments quickly, then that's a problem. Another issue here is that it's quite difficult to configure them. So if you think of a conda environment where you can have a config file, there are ways of doing this for virtual machines, but it's quite cumbersome, and it's not as straightforward. Because you're essentially installing a new operating system with all of the additional software that you need to run your experiments every time you create a virtual machine. Now, a really big part that differentiates virtual machines from the containers that we're going to talk about is that you can see here that this layer of OS, or the kernel, is duplicated between the virtual machine and the host computer. And again, the reason for this is that what we're doing here is called hardware virtualization. So we're exposing the hardware to the virtual machine, but that means that the operating system or the applications that you install in your virtual machine need to talk to their own kernel. So there's another kernel in the virtual machine, and it talks to the virtualized hardware. So it needs to understand how to talk to a processor and the memory and so on. And then that talks to the hypervisor, and that hypervisor talks to another kernel, and that then talks to the actual physical hardware. So this whole layer here is duplicated. And that's really one of the main ideas of a container, is to not do that, not duplicate this. And there are a number of other downsides for virtual machines, but the important part to remember here is full isolation. What you're virtualizing is the hardware, and it can be very nice for testing things, especially if you're testing with respect to hardware or different types of operating systems, and you need full isolation. Okay, so what are containers then, if this is what a virtual machine is? Well, the idea of containers is, just as I said, let's not duplicate the kernel, right? So we have hardware, we have the operating system or kernel, and then what we can do is we can just create an environment that is using, or all of these environments are reusing the operating system or kernel on the host. Now that has one important implication, and that is you now cannot run a different type of operating system, and so let's say Windows or Linux, inside a container compared to what's running on your host computer. So typically, the vast majority of containers are running on using the Linux kernel, and so the host computer that they're running on has to use Linux. Now you may ask yourself, well, how is it that I'm on a Mac and I can use this? That's because what you're doing under the hood is you're really running the container engine in a virtual machine, and we can talk about that in the lecture. The important thing to remember here is a container shares the host computer's kernel or operating system. A virtual machine does not. And this is very nice. So now we're calling this is not hardware virtualization, this is operating system virtualization, because the operating system, the kernel, is represented virtually to these environments. And the container itself still thinks that it's in its own environment. It cannot see outside of the container. It cannot see as easily, or it cannot see easily the resources or the things on the host computer. And you can still install your applications or your dependencies in each container separately. They're fully isolated, but you're always sharing the operating system kernel. And now we're in virtual machine land, we were using the hypervisor. What we're using here to make these containers is called the container engine. And one of the most widely used container engines is Docker. And Singularity is another one that we'll take a look at the end of the lecture. So one way of thinking about this, or this is not the most technically accurate representation, but one way I like to think about it is if you're in virtual machine, you're in a house, you duplicate the whole thing, plumbing, power, all the rooms, air conditioning, heating, whatever you need. So if you're in your house, you're not in your neighbor's house, there's nothing related there. The only thing you share is, I guess, the physical foundation of part of the city you're in. Now, a container is more like a voting booth, maybe, in the sense that the way that this isolation is accomplished is that all the containers are sharing the same operating system under the hood, but you're encapsulating them in a way that other containers cannot see processes and resources inside your container, and you cannot look outside. So this is something called kernel namespaces. That's not so important for the lecture, but essentially you're cordoning off a section, and you say, okay, this is for my container, and everything inside the container is isolated, cannot look outside, and has different identifiers and so on. Now, the reason, so for Docker, the thing that we're talking about when we talk about Docker is really two things. So there's the Docker engine, or the command line program that we use to start and build and stop and resume containers. And then there is Docker Hub. So it's a website. It's called it's a container image, as a Docker image repository. And this is a little bit like the relationship between pip and the PyPy. So with pip, you install libraries, Python libraries, and they're hosted on PyPy. And it's a little bit like this with Docker Hub, where you can share Docker images on Docker Hub, and then you can pull them and run them and build them and commit new ones back to Docker Hub. Now, what I want to mention here is that Docker Hub is not the only image registry. It's just one of the more popular ones. It's a commercial application, so they charge you for certain features. And there are other ways of hosting Docker or container images. Now, you already see me struggling a little bit with this container and images here, because that is sometimes not clearly delineated. And so I just want to make that part of the terminology very clear, because that is initially often confusing. So the way that they are different is that if you create a Docker image, what you're creating is a specific read-only snapshot. So that means it's almost like a frame in a movie, right? So you're taking a specific point in time and you're saying, okay, in this point in time, my environment is using the following dependencies, is using this distribution version, and has these files in it, and so on. And they're organized in layers, which is a very attractive feature of Docker images, because what that means is if you have two different images and they share some prior dependency, let's say they both need Python of the same version, then you can have only one copy of this image layer that they can then both build on top of. And where in Conda you have the Conda environment.yaml file, or the Python requirements.txt, the analogous recipe file is called a Docker file, and we're going to take a look at one and make our own a little bit later in the course. So compared to the Docker image, the Docker container is what happens when you take an image and you start running it. So you can have one image but many containers that are launched from that image. So that's almost like taking that frame and then bringing it to life and make a movie out of it if you want. So it's a live instance, and it's not read-only. It has a container layer that you can write into. We're going to see why that's usually not a good idea to write into this layer. And each container that you spawn from the same image is fully isolated, so they have nothing shared with each other, that they can't see each other by default, and they can't access each other's processes and so on. So they're fully isolated, but they all spawned from the same Docker image. And that's very useful because you can run several instances of the same thing very easily, very quickly with just a single command. And that is a big difference from the virtual machines, for example, because running a container is very cheap once you have the image. Okay, so how can you do this yourself? Well, there are two ways, and we're going to look at both of them. The easiest one is you use an image that somebody else has already made. So the best way to do this is to go on Docker Hub and find an image that you're interested in, and then just pull it, and that brings it to your computer. And the other thing that we're going to do a little later is make our own image. And you can already see this is kind of the recipe that I said. And what you see here, this from, is that you're starting from someone else's image. So you don't have to start from scratch, which is a really attractive feature. So you start with an image and then you put another layer on top of it. This is kind of how Docker images work. So you start with the layer of Ubuntu, for example. Okay, let's run one container. The easiest one to start with is the one from the tutorial. So there's on Docker Hub the Hello World image, and you can take a look at the site. It's not that much information in it. It's just for the tutorial. But what you can already see here is that there's this tags tab, and you can see that there are different tags for the same image, and that's quite important. Those are like versions for your libraries, so you always want to make sure that you pull typically a specific tag. Now this is maybe an exception because it's the tutorial one, but let me show you what this looks like. So I have my VS Code here, and I'm just going to run the command from the slides. Actually, I can show you my slides at the same time. So here it says docker pull hello world latest, and so I'm going to do that. Docker pull hello world, and then latest is the tag that I want to pull, and so I'm going to pull this, and it's quite quick. Now, where did this go? Well, it's somewhere on your computer, but you can see here that I just pulled the image. When I run Docker images, I can see that this is one of the images that I've just pulled. And there's some other images that I already had on my computer. Now, if I want to run this, the way to do this is I say docker run. So let's take that, docker run, and then hello world, latest, and then it runs and shows me a bunch of things. And it says this seems to work correctly, and it's not really doing anything else. It's not very useful, but this is how you run an image. So somebody defined this, and I made a container out of it by saying docker run, and that container did print some stuff, and then it exited again. Right, so how about we find something a little more useful to do? Let's imagine I'm a student that comes to the course a little late, and I didn't really follow the setup instructions, and it turns out I do not have Conda on my computer. And that's very sad, and I could go and install all of this, but an alternative solution is I could go to Docker Hub and search for Conda. And so it just so happens that the people who built Conda Continuum Analytics have created a Docker image. Now I can't seem to find the right one, so I'll use my nifty little link here to go to Miniconda 3 for Python 3. And again, here you see a page and you see some tags, and this time I actually want to pay attention to what tag I pull, because there are quite a number of them, and I want to make sure that I have the right version. And I think I wanted to have 22.11, and there are two of those. One is Alpine. Now you don't need to understand all of this, but what this means, or what this tells me, is that this is built on top of the Alpine distribution of the Linux kernel. So you may be familiar with other Linux distributions like Ubuntu or Debian or Fedora, and Alpine is a very, very bare bones distribution, but it's very nice for containers because, as you can see here, it's very small. And now I clicked something and it's scrolled somewhere else. Let's get back. Another nice feature that I wanted to show you briefly is when you click on the tag on Docker Hub, you can actually see the different commands that were executed in order to create this specific image. And that can be quite useful. It's also, sometimes you can actually see the Docker file, which is even more useful, but you can take a look, and there are the commands that you can run locally to do this too, but let's not get ahead too much of ourselves. So I now want to pull this specific version, and I will do that, and it will download it to my local host. And then I'm gonna go back to my slides to see what I'm supposed to do. I need to run this now. Okay, so let's download this, and then images. There it is, Miniconda. And I'm going to Docker run Continuum Alpine. Okay. So I'm running it, and nothing happened. Okay. Well, that's not great. Why could this be? We're going to see this later, but every image has a default command that runs when you don't provide it any additional attributes. And in this case, the default command is probably just a command line, and nothing happens on its own. It doesn't work like the Hello World Docker image that actually prints something if I just run it. So what we can do with these types of images that are more meant as base layers to build on top of, is that we can connect to it using the interactive terminal. So there's a flag IT, and now when I run this, I will not just run the container and then have it exit immediately, but I will instead connect to it, and now I'm dropped into a interactive terminal. So you can already see here that it says base. You may remember this from your own Conda installation. And when I do things like hostname, I can see that I have this weird number here that you can also see here. So I'm in a container. My host name on the outside is different. And now if I run Conda, I am not getting an error message because Conda is actually installed in my container. So I could go and use Conda and do all the things that the course wants me to do. Now I can disconnect by saying exit, and then I'm back on my computer just to show you that I wasn't lying. My computer has a different name, and also Conda is not installed. Okay, so that's one nice thing about a container. Now let's connect again, this one I already showed you, but let's connect again and try to see whether we can access files. So here I'm on my host computer. It's called Docker Place, and I can create a file. Touch file on my host, and so I can see this file here. And now if I Docker run again, I can do an ls, and I see something different. Okay, well, it might be that I'm just not in the right directory. Let's try and go to documents, Docker place, and it turns out this does not exist. So what I'm trying to show you here is that the container cannot see the file system of the host computer unless you do some very specific commands. And that is important to remember, because if you want to use files that are on your computer when running inside the container, you need to remember that you need to expose those paths to your container. Okay, so while we're still in the container, let's try something else. Let's go to, I guess the root directory is maybe a good path, right? So where are we now? Yeah, we're in the root directory of the container. That's not a place you typically want to create files, especially not on your host computer. But as we'll see, inside a Docker container, by default, I'm always root. So you can see here that I am the root user, and the root user is similar to the administrator if you're more familiar with Windows, and this user has elevated privileges, so I can do whatever I want, and that makes me very dangerous, especially if I don't know what I'm doing. Now, inside my container, the only thing I can break is my container, but it's important to remember that the root user is a special user, and you don't want to be running around as a root user if you can avoid it. And I'll show you at the end of the lecture how to make Docker containers run as not root. But let's just say I make a file, touch file in my container. And so now in my root directory, I have this file in my container.txt, and I can see it. And so now I exit my container, or I can also use Control D if I'm lazy. Now I can go and try to see this file in my container.txt from my host computer, and again, there is no such file or directory. Okay, so it works. It doesn't work both ways. I cannot see what's in the container cannot see what's on the host, or the host cannot see what's in the container, and the container cannot see what's on the host file system. Now here's a tricky question. What about the file I've just written to my container? So let's take a look at that. Let's relaunch the container and go to where I just created this path, root, and then do ls, and the file is not there. How is this possible? Because we just wrote it and I said that the container is writable. Well, the very, very important thing that I want you to remember is that when you write to a container, and you shouldn't do that in most cases, the file that you've written is tied to the specific container. Now, I said before that you can launch a number of containers from the same image, and if you look closely, you will see that the number here, the host name, has changed from when we last ran this. And the reason it has changed is because I'm in a different container now. Every time I run container, I do the docker run command from a specific image, unless I define it otherwise, I create a new container. And so this container does not contain the file that I've created before. And what that immediately tells me is I should not store my experiment results inside of a container, because essentially you need to treat the files that you could write to a container as very temporary and easily destructive. So just to show you where all this is, if I take a look at this, Docker PS shows me my currently running Docker processes, and they're non-running, but if I do -a, I see also the ones that have already exited, and here you can see that I've made quite a number of these the conduct containers, and so it probably was in this one that we wrote the file, and then we launched this one afterwards. The important thing I want you to remember here is the host by default doesn't see what's in the container doesn't see by default what's on the host, and if you write inside a container, those files are very, very temporary, and there are a number of cleanup operations that will just remove stopped containers, and then your data are gone forever. So don't store things inside a container. So how do we actually share data between the host and the computer, the host and the container? Well, we can use something called a mount command. Excuse me. So if I go back to my docker run command, then I can use an additional flag here. It's called -v. And I can say, okay, well, this place that I'm currently in, documents docker place, I want that to be exposed to my container, and specifically I want this to be exposed to a path that is root/my dir. I like that path. I can choose whatever I want, and this mount command will bind the location on the host to the path in the container, and it will create the directory mydir if it doesn't exist inside the container. Now, it's important that you make sure that this starts with a path. There is another way to use -v that we're not talking about, but if you have some errors, just make sure that there is a path in the beginning, because this might also be misunderstood as a volume, which you can look up what a Docker volume is. Those are also useful, but we're not going to talk about those today. Okay, so now I am in a different container, again, different ID, and I can see that in my root directory, I now have this directory here, mydir, and if I go in there, I can actually see the file on my host. And if I make a new file, and I say file from inside container, I can see both of them, and then if I exit, I can also see the file that I have just created in my container. Now you may notice that the file that I just created was created as a root user, and that's the default, and there's a reason that we can talk about why this happens, but I am creating files on the host operating system with the permissions of the user inside the container. And that is one of the issues that Docker also has, that there's a problem of elevated permissions, and we'll talk about that later when we talk about Singularity. But keep this in mind, because you may create files as root, and then when you delete them, you will need to also use elevated privileges to delete or write them. Okay, so this is how I connect to files in my container. This is a little summary slide of what I've just done. But now you might be wondering, okay, this is great. I've used an image that somebody else made, but I want very specific environment characteristics, and there might not be a specific Docker image like that in the world. How do I make my own flavor starting from something else? And that's exactly what we're going to do. So you remember module 8, where you learned with the first part of the machine learning lecture, and you wrote this script, or I guess you've seen the script, to do classification using the abide dataset. Now in the Git repository that I have created, oh wait, I have forgotten to show you my slides. Yeah, so I just shown you the summary, and now we're at exercise 3. So now we're trying to containerize the classifier by making our own image. So in the Git repository, you have something that roughly looks like this. I think you also have a Docker file, but that's just an example. We're going to make our own now. And what we want to do is we want to create a Docker image that can run this classification script in an isolated container, so I don't have to create all of have to install all of the dependencies that the script needs to run. Okay, so how can I do this? Well, I'm going to use going to create a Docker file. So if you already have one, throw it away or start from scratch. And I'm going to show you how Docker file works. So the first thing we want to do is we start from some existing image. Now, I could go on Docker Hub and look for images that contain the Python version that we're using in this course. I think it's 3.9, but I happen to know that there is a official Python image that has 3.9, and you notice the -slim here. That's a little bit like Alpine. It's just a slim version of Debian, so we don't make a very big image. Now what this means is that my base layer is going to be built on top of this image that has been created by somebody else, and now I'm going to add more things to it. Every time I add something, I make another layer. So here I need this, I need to install my Python dependencies, right? Because if you remember the setup instructions, you could also go and look at them. There are a number of Python dependencies you want to install. You could use conda for this, but I'm not going to. I'm just going to use pip, because otherwise I would need to get all the conda stuff in my image as well. There's this little extra flag here that says no cache dir. The reason for this is that Docker is really good at caching these layers on its own, so we don't need to use the Python caching of dependency installations. Okay, so now the run command should install all of these Python dependencies into this environment, and by doing so adds another layer. And then I have this workdir command here, and what that does is it creates a new directory inside the image, calls it predict, and then also changes to it. So this is now my default directory. If I start the container, I'm going to start in the predict directory unless I specify something else. And as my last command here, I use copy, and copy takes a file on my host computer and copies it to a specific path in my Docker image. And so just to show you what I'm copying here, this is the script that does all of the predictions. And then the last thing I do is I specify a command, and we're going to talk a little bit about what that is, but that's essentially, if you don't specify anything, this is the thing that runs. So if I don't specify anything, I just want my terminal, I want a bash shell to be run. Okay, cool. So now I've made this Docker file, and now how do I build this? Well, I need to use Docker build. Actually, let me switch over to this place here. So here I have my Docker file that I've just created. And I now need to run Docker build to make an image from this file. And whoops. The way this syntax works is you write Docker build, and then if you remember, so now I want to give my image a name, so that's called tagging it, and I'm just going to say my QLS image, and if I don't provide a specific tag, it will automatically get the latest, and right now I think that's fine. And the last thing that is very important to miss in the beginning when you just learn Docker is I need to tell it where my build context is, or where to build from. And that, let me just reset my command line so you can see what I'm doing here. So build -t my QLS image. And then I need to give it the build context is what it's called. And I'm just going to put dot, and if you remember the bash lecture, that means the directory I'm currently in. Okay, so now I'm going to run this, and it does some things. So it will fetch the Python layer that I'm building from, and then it runs the pip install here, and it'll copy over the file, and then it will finish, and I will have locally built this image. And if I were to run this command again, it would go much faster, because unless I change something about the dependencies, the Python dependencies here, this step would not have to be repeated. Okay, just gonna pause the video here until this is finished. Okay, so now I've built my image. Took a little while, but it's now done, and I can take a look at it. Docker images, and here I see my QLS image latest 20 seconds ago. Okay, so I deleted the old ones. Cool. So now I can run this. Let me just give you the slides again. I can run this now and try to attach to it again the same way that we've done this before. So just see here, you can actually see what I'm doing. Aha, yeah, sorry about that. I realize you might not have seen the lower half of the screen. You should always see the commands on the slides as well. So now I want to run my new image. So I'm just going to show you again. Here it is, my QLS image. And I will run it now, but I will also immediately attach to it because I already know that I'm also otherwise just going to get a command line. And so I'm going to use my QLS image. Okay. Yes, and I forgot to put the run command, so that's why I didn't do anything. Okay, so run and then interactive terminal, my QLS image. Okay. So now it drops me inside of this container, and I am root again. And I have this directory called abide classification. And now I can go and say Python abide classification and just run this. I'm trusting that all of the dependencies have already been installed and it is doing things, which is very nice. Now, you may already notice something here, which is that it's downloading a bunch of data. And I don't want that right now because I think by default it downloads 100 subjects, and that might take a little too long for me right now. So I'm going to abort this with Control-C, and instead I happen to know that this script is taking command line arguments, so I'm just going to say number of subjects and then let's say 5, right? So now it's going to only download 5 subjects. It spits out a bunch of warnings, but here I see only 5. And then obviously this does not work with only 5 subjects, but you can see that the whole thing completes. Okay, so that's great. I've just created the environment that allows me to run the script. I've put the script in it, and I can attach to the container and run the script. And I didn't need to install any of these things on my local machine. That's very nice. Another way that I can do this is instead of attaching interactively, I can provide arguments to the container. So I can just say the same thing, abide classification and then n subjects 5. And this will also work. Now, the reason this works is because if I provide any arguments to the Docker run call after my image, then those will override my default command. So the bash command that I've defined in my Docker file script will be replaced by this Python thing. And again, you can see the whole thing ran, and it needed to download the data. Okay, well, this is great, but now I have to write this Python abide classification and subjects every single time I run the command. I want to run this image, and I don't want that because I'd rather not. And so what I can do is I can update my Docker file. So rather than having my default command be bin bash, I can instead say I want my default command to be Python. And let me just take a quick look. I don't want to write all this by hand again. So here we go. Rather than bin bash, I just want the thing that we've just written. So I want Python to call the specific script in this path and then give it an argument 5. Now, you will notice that each individual command here is separated into its own string, and that is the syntax for this command. You can also write it as a single string. If you go and check out the Docker documentations, there are good examples for how you use CMD. The important thing to remember is CMD is the default command that I want to run if the user doesn't provide their own command and thereby overrides this. Now if I save this, I'm not done yet because my image still is the same image from before. So if I look at Docker images, it still has my timestamp from 7 minutes ago. So I need to rebuild it, but that's easily done. I'm going to, again, Docker build, use the same image name, and then this time it will go much faster because I didn't need to build most of the layers. I just needed to change the command. And so now if I do Docker images again, it should be updated. Yeah, and so it's updated. I have now moved my tag my QLS image to this new hash that is using a different command. So now if I run Docker run my QLS without any arguments, instead of just getting my command line, I will actually run the whole analysis because I've specified it in this way in the default command. And I noticed that in this view you can also not see my whole screen, so let's fix that. Okay, so here's the command that I ran, Docker run my QLS image, and it runs the entire script. And that's very nice. Now I don't need to type the same thing every time I run my Docker image. So what we've done so far is we have created a Docker file. There you can see it. And we have defined a custom command. That was the last thing we did, so that rather than jump into a shell, we immediately execute the classifier with the right parameters. And then we've built our image so that we have it locally, and then we can run Docker run and point at the image name, and it will create a new container and run all the things in this specified environment. And that's great, but you may have noticed that every time we do this, we download a lot of data. And in the beginning, I said that it's not a good idea to download or to store data in a container. Now, in this case, the reason it's not a good idea is because it's wasteful. Every time you make a new container, you need to download it again. And most of you have already downloaded those data on your home directory or on your local computer because you've done the actual modules that use these data. So we already know how to deal with this. We can use volumes. So this is what we're currently doing. We're downloading data, running the script, and then we have all the insights and outputs inside of the container. And the container isn't for storing data, it's for isolating processes. And so rather than doing what we've just done, we should keep the data outside of the container and just bind mount it into the container, so the container or all containers that we run can share the same data on the host, don't need to download it again. Okay, and we know how to do this, but just as a reminder, what we're going to do is we're going to mount the path where the data are on our computer. So I'm just going to show you that I have this in my home directory. There is a nylon data, and it has the abide PCP and the preprocessed connectome project. And now when I run my script, I can mount this path. So I can say home nylon data, and then I mount this to the path data in my container, and I provide the image name, my QLS image. And so now I could just let it run like this, but the problem is, if you remember, that our custom command doesn't say anything about where to take the data from. So it'll use the defaults of the script, and the default in the script is just to expect it in the home directory. But I'm mounting the data in my path to the path/data, root data. So I need to explain to the container where it can go and look for the data needed to run the script. So I'm going to look at the command line argument for doing that, and that's called data dir. And I will say data. So now I'm running my command, my Docker container, having mounted the data into the data directory inside the container, and then I'm telling the container run the script and get the data from data dir. And so when I do this, I will see that it will not download data locally first. It still spits out a bunch of warnings, but it ran the whole thing. And yeah, well, you have to believe me, it didn't download any data. It used the data from my home directory. And if I do this again, I'm launching a new container, and again, that container will use the data from my home directory. Now, one of the things you will notice is that when I scroll up here, somewhere it says, yeah, here, number of samples, that's now 100. And if you've paid attention so far, then you probably understand why that happened. I have in my Docker file the argument n subjects 5, so you could think, well, this should have only 5 subjects. But because the way I have run my container is by providing my own custom command here, this overrides the default command and therefore ignores whatever I have set as n subjects. And so again, the default in the script for n subjects is 100, so that's why it's using 100 subjects. If I wanted to set that again, then I could do it like that and say n subjects 5. And then it's going to use only 5, but still use the data from my host computer. Okay, so that's very nice. Then what I've done so far is specified the environment with my Docker file, and I've made an image, and I've put the script in it, and I have created a default command. And if I'm being nice, I could even add here the data dir data, and then say, okay, please don't forget to mount the nylearn data directory to /data in the container. And then you don't even need to update the command, you can still use Docker run. So I've done all these things. I've now containerized my classifier application or my script. And that's very cool, because now I can go and share it with somebody else and say, here is the classifier that will predict autism for you. Just use Docker run and you should be able to replicate all of the great findings that I've done. Here's one catch that I want to quickly go over with you. What if you want to make a change to the code? And that's not so rare, right? So what if I wanted to do, let's say, this? Here it says analysis completed for something, something, something. And I wanted to end with something else. I wanted to say, hello QLS lecture. Okay, so if I save this and I run my script again, oops, I want to use the one with the data. If I run my script again, I'll let you think for a second if this should show up, this new print message. But the main point I'm trying to make is it will not, because I've made this change to the print statement on the file on my host computer, so a byte classifier on my host computer. But if I go inside of the image, or if I use the image to spawn a container, inside the container, it's still the same file that I've copied over during the build step. And that file did not have this extra print statement. So now you might think, well, that's not great, because what do I do if I want to change the code? Do I have to build every single time? And especially if you're using Docker for development, which is a really good practice, this would be very annoying. But there is a nice property that these mount containers have, and that is they will create the path that you're mounting into on the container, even if it already exists. And what that means is that if I use the path /predict to store my my script, so as you can see here, I have this work directory predict, and I copy the file into the predict directory. A trick that I can use is I can mount my local source code into the container over the same path. and I'll just show you that in a second because that's really useful. So let's not get ahead of ourselves. So rather than just running the container like this, and I'm not rebuilding it here, I will make a second mount statement, and I will say use my local directory that I'm in, so tier containers where my abide classifier file is, and mount this to the path in my container that I'm running my script from. And so if I do this, I will now not use the file that I have copied into the container, but I'm actually using the file that is on my computer. And you see here now it prints the hello QLS lecture. And if I keep changing it without rebuilding anything, I can see the changes immediately. And that's a really useful way of combining the development and the sharing of the Docker container, because now this script that I am editing here on my computer, where I don't have any of the correct dependencies, is still running in this controlled environment that I've built with my work directory. And when I go and do Docker build, I will just copy over whatever the most recent version of abide classification is into this predict, and then the user will say Docker run, and they will always use the most up-to-date version. And I've also developed in the same environment, so I know it'll very, very likely work, and that's very nice. Okay, so that's essentially the workflow for containerizing this classifier, and as you can see, it wasn't very difficult. We have, created a couple of lines in this Docker file, and it worked very nicely. If you do look at the file that was in your Git repository, there's a portion where I create a specific user, and then make that the default user inside of the container, and that is a way that you can make your container run without root user privileges, and that is generally a good idea. Unless your software actually needs root user privileges, you should create a user. So I think I've just deleted this file here, and I could probably just restore it. Let me just get rid of my local, and then restore Docker file, and then we will see in all its glory the file that you have, and it looks very similar. The main difference here is that I create a user group and a specific user. I'm calling it QLS user, and so the trick here is if I build this, then I will not be root in any container I spawn off of this image. So if I do Docker run my QLS image, then I will be the QLS user inside of this container. And that's quite useful because, oh, right, yeah, I forgot to mount the, let me just overwrite this. So here you can see that I am now not the root anymore, but I'm the QLS user, and that's quite useful because the files that I create inside of the container, they're really not using the username, they're using the user ID, and typically if you're the only user on your system, your user ID is going to be 1000, and if you use this user ID to create files, it'll look outside like you've created them with your host user. But that's just a little hint. You can go and look in the Docker documentation to see how to do this in more detail. Okay, so we have done what we have set out to do. There's really only one thing left that I want to talk about here, and that is what should I do if I end up running things on a supercomputer. And so the supercomputer environments like Compute Canada that you will see in the next module, they don't allow you to use Docker. And they want you to use Singularity instead. Singularity is also a containerization solution, but the main reason that they don't like you to use Docker is because if you remember the differences between Docker and a virtual machine, Docker isn't as isolated as a virtual machine. There are ways of escalating your privileges and doing things on the host machine if you're running inside of a Docker container that would be beyond the things that you should be able to do, let's say. And so essentially there's a security problem with Docker containers if you run them as root. Now, as I've shown you, you can not run them as root, but as a general rule, on shared computers, like a supercomputer, high performance cluster, they will not let you run Docker for this exact reason, because they cannot prevent, or they cannot guarantee that you wouldn't do malicious things from inside of your container. So instead, people tend to use Singularity. Singularity is now called Apptainer. So most documentation will still refer to it as Singularity. If you want to install it, you typically have to search for Apptainer. To make things even more confusing, there is still a Singularity Community Edition. And they're kind of doing things in parallel. The important thing to remember is Apptainer or Singularity are the containerization solutions for high-performance clusters or shared systems, supercomputers. And here's some docs from the Compute Canada website where they explain why they prefer Singularity, and the most important one is that this is a secure way to run Linux clusters. And that's really the main reason. There are some other nice features, like exposing your home directory by default and so on, not running as root. And so now you might wonder, well, why did you tell us about Docker when most of our things are running on the high performance cluster? And the trick is Singularity really can be the last step in your process. So the recommended way of doing things is you develop in Docker, you make your Docker file, you build your Docker image, and when you're finished, when you think this is good to go, I can scale it up on the high performance cluster where I have all the resources I need, then you push this image that you've built to Docker Hub, and then you can pull it with Apptainer or with Singularity from Docker Hub and make a Singularity file out of it. So I'm just going to show you this very briefly here. Let's go to the other terminal. So I don't have a file here, so I could say I have Apptainer installed. So Apptainer should work. There you go. And so now I can say Apptainer pull, and then Docker, and actually I'm going to use just Ubuntu, the Ubuntu image, and I'm just going to pull that. So now what this will do is we'll go to Docker Hub, and it will take the Docker Ubuntu image and it will make a SIF file from it, and so that's by convention the file ending for a Singularity image file. That's another important difference between Docker and Singularity. Typically, you will not see the actual image file, the image that's being created with Docker, but with Singularity, the actual image is a file that you can, move around and copy and run. So now if I do Apptainer run Ubuntu, well, I just get dropped into an Ubuntu distribution, but you get the idea. It's the same general principle as a Docker image, and this is a controlled environment that was specified as a Docker image, but I'm running it as a Singularity image with different permissions. And that's really all I wanted to share with you. The important thing to remember here is that containers are a great way to isolate and specify environments that include more than just your Python or R dependencies that go down to the level of the operating system and the specific libraries that are installed and other software that might not be written in Python or R. They are a great way to spawn up a number of similar processes. And they are isolated from the host and each other, but they're not quite as isolated as a virtual machine. So there are some use cases for virtual machines, specifically with testing. Because of the isolation of containers, you need to explicitly mount paths into the container if you want to share files between the host and the container. And lastly, once you're ready and want to deploy the code or application that you've written, if you wanted to run, and I think maybe you will do this, if you want to run the classification Python script on the high performance cluster in a containerized form, you would do this with Singularity, right? So you might take the image that we've built, pull it from Singularity, make a Singularity file, and then run that. And if you want to build your own file, this is something you do with a Docker file. And the very attractive, nice thing is that you don't need to start from scratch. You can start with somebody else's image. And that's really the main reason that these images like the mini Conda one exists. They're meant as a starting place for you to build your own image, right? So if you don't want to specify in your Docker file that you need to install Conda, you can just take this one and you know that Conda is already installed. And you're good to go. There's some other tools, specifically NeuroDocker I wanted to mention, which is a way, it's a tool that you can use to build Docker files, because it can get quite repetitive. The one that we've written was very simple, but there are a number of things that you might want to install, and then you don't have to type all of this out. You can use NeuroDocker to create these files for you. And here are a number of additional resources that you can take a look at. And I hope this has given you some overview of what containers are and how they work. And I'm also hoping that you're excited to try them out and use them in your own research, because I think that's a really good idea. And I'm looking forward to seeing you all in person during the lecture. Okay, bye-bye.